think I'm going to point my phaser in this direction. I think that's the right way to point a phaser. I'm really happy to be here with the Academy and in this wonderful environment. We've been looking at how human brains respond to architecture, and I'm going to describe how an understanding of nervous systems can inform architecture that has nervous behavior built in. Certain problems seem easy for living systems to compute, but they're curiously difficult for manufactured systems to mimic. Walking, for instance, it seems simple, but it was devilishly hard to make a machine do it. A variety of gaits animals use when they negotiate varied terrain has been among the more difficult behaviors to model successfully. This is a chair with 3 different gaits. I'd like to build one like that. Understanding how legs work involved mathematical investigations of the nature of oscillations and their supple variety. And this is the phase space for a real cat's leg. Coupled with this was another insight, that walking was fundamentally a lower behavior, not solely in the brain, but also in the spinal cord, involving electrical activity that was somehow simpler. The cat had some bad luck, but we did learn something from it. To understand this simplicity, imagine the growth of nerves in very primitive animals, starting with the first evidence of coordinated nervous activity in cells. The ancestors of neurons may have been slightly differentiated cells in creatures that were the precursors to sponges, jellyfish, polyps, and hydras. Some of these individual creatures are more like a neighborhood of cells than a singular organism. In them, we can see a functional nervous net or ring in its regular nervous oscillation. For instance, a jellyfish needs a coordinated set of nerves that can communicate with each other, slowly propagating nervous waves at about 20 centimeters per second as it rhythmically moves to ingest water and food. Circuits comprised of decentralized ganglia apparently underlie locomotion in animals from across the phyla, from the cockroach to the lamprey to the higher mammals. The mathematical topology that seems to underlie these neural mechanisms has been modeled in a variety of ways. For instance, the behavior of such a nervous net can be modeled with a circular chain of simple electronic components that propagate electrical pulses with variable delays. And that's one of them. These pulses can be introduced and controlled by a capacitor and a resistor that hold and release electrical pulses. This is analog behavior, but it can also be modeled digitally. Repurposing genetically predisposed designed mechanisms is at the root of a lot of evolution. Once we understand this simple autonomous nervous behavior, it can determine the development of an architecture with performance that is driven by external events. The savvy designer's emphasis is now on the kind of intelligence that can be seen in a loose grouping of dumber, not smarter, electronic controllers. And that's one of them. Colonies, crowds, and flocks offer a window into the kind of behavior that isn't programmed and computed in a traditional way. The colony's members don't have to be particularly smart, because when large numbers of them communicate with each other in networks, a new kind of intelligence resides in those interconnection patterns. Simple individual behavior protocols can lead to the larger scale emergent behavior of this kind of ecology of objects. Now let's see. My research projects use decentralized weak computation in a sort of autonomic nervous system. I believe this kind of control will pay benefits of robust behavior and behaviorally designed event-driven architecture for the same reason that it has paid dividends in walking systems. In my prototypes, I do use discrete electronic components because they're easier to work with. And in design, I design with an eye toward the time when some of these electronics can be manufactured as an integral part of the building component we want to make sentient, alert, and responsive. I'm also interested in energy grazing systems that only use what they can get easily and naturally from what's already around them. That's parasitic, but low impact. I want these new projects to feed naturally rather than being fed intravenously. The first 2 projects I'll describe is a nervous wall system, and it's the one I'm working on right now. It's an architectural component being prototyped as an interior system for exterior walls, but it could be developed into an exterior system. In it, low voltage direct current power collection, sensing, logic, and power usage are distributed into a field of small independent units throughout the component. It's designed to sense the direction and intensity of light and temperature as they change around a glazed building, and to open, angle, or close its fabric as appropriate to best capture solar energy, let in light and views, and also to prevent excessive radiant heat loss. Coming up on dusk, in the night. The first version of this project, which I did a few years ago, a basic nervous net of electronic buffers, oscillates at variable rates, and these provide a specialized wave pattern that a standard servo motor interprets to move to a particular rotation. The oscillation rate is much slower than normal for a servo, about as slow as a quarter of a second, 1/16 of the standard pulse speed, because that reduces the electricity that's needed for logic. You can just barely hear that. That's the speed of the servos operating. Changes in light and temperature that move along the fabric of the piece during the day are interpreted by different kinds of sensors, giving a variable pulse delay in the net that changes the angle of the servo, which modifies the openings in the fabric of the piece. Because the servo is a gear motor, it holds its position even without electricity. Power can be gathered very slowly and intermittently and stored in high-capacity capacitors rather than in batteries for short bursts of nervous activity and motion. In a sense, the nervous net represents a benign colony of independent agents that sleep, wake, notice, act, and sleep again. The first version operated okay, and it moved effectively when it had stored enough power from the sun, and it rested effectively when it had no power. In this early version, oscillating buffers drove the servos slowly by noticing conditions and changing the oscillations they sent. It caused the servos to thrash a bit, and that noise that you heard was a little bit of the thrashing of the motors, and that used more power than was absolutely necessary, and that in turn sometimes overloaded the ability of the supercapacitor storage, which has a high internal resistance. The second version, which I'm fabricating, I'm using simple program microcontrollers with ultra-low amperage sleep states. The behavior still involves waking, sensing, and communicating with the servo in swift bursts, and then turning off the logic power and the motive power in the next wakeful state. This saves even more power than those intermittently oscillating buffer design, and the short purposeful bursts of motor power do not overtax the amperage of those large capacitors. Right now I'm fabricating small independent exterior skin nodes that will collect and store solar power as low voltage direct current potential and completely off the grid. These skin nodes are going to come in two flavors, one which will have the ability to discharge the electricity all at once when night happens, and the other will have the ability to discharge electricity occasionally during the day as is needed to change the angle and follow the sun. This last project I'm going to show you, Flocking Lights, was installed for a demonstration at the National Center for Supercomputing Applications in Urbana, Illinois. It's a field of lights that take their low voltage electricity from a pair of wires strung across a ceiling, which is a pretty common system. These lights parasitically borrow some current for their logic and motive power, and they move around independently looking for things to illuminate. It turns out they especially like to illuminate bald heads. Let's play that one. You'll see them finding my bald head. Can you click that? Thank you. That's the steady state. There I am. They found me. For once, it's a pleasure to be bald. I can imagine a flock of a future generation of these lights moving fluidly through a building, providing illumination where it was needed. Each pair of low voltage wires holds two identical lights, which increase the social interaction between the lights. I say social interactions because a field of lights needs to be trained to overcome individual manufacturing and aging variances. And they need to play well with each other, and they need to communicate with each other in order to flock. Occasional antisocial behavior also develops. When enough agoraphobia or bullying behavior becomes evident, the whole system needs to be rebooted, and every light needs to be retrained. This happens once a day overnight, so the entire system acts like a small self-contained universe oscillating through regular big bangs. The universe these lights inhabit is initialized at power on with discovery and training functions that can be seen as calibration or a kind of socialization process. I'm going to read through that and then show you the socialization process. Each identical neonatal light figures out its own handedness within a few milliseconds of each life cycle. It looks to the left and it looks to the right, and it either sees something like itself or it sees something like a wall. Each neonate then remembers its place in the universe. Those that are right-handed know to wait, and those that are left-handed know to the next phase of their universe, which is speed calibration. Speed calibration is necessary because the light's components have sloppy manufacturing tolerances and they age differently. Each neonate has a different internal friction to work against every single time the universe reboots. In this phase of the bootstrap, the lights race back and forth, sometimes faster and sometimes slower, always comparing the time it takes for to traverse to an idealized platonic behavior. During this phase, the lights avoid collisions with walls and neighboring lights using the same sensors they use to first determine their own handedness. When each light achieves the right speed, its next task is to determine and remember the average light in the universe. The average light of a universe can vary with the seasons, and understanding that average makes looking down for the extraordinary things below much easier. The average light level is determined by one special traverse where the lights run with rapidly flashing LEDs for observers outside their universe to enjoy. Once the left-handed lights have finished their calibration, they go to the sideline and wait for the right-handed lights to wake up and start their own calibration. Differently handed groups of lights need special calibration because they need the whole length of the run without sharing. Once every light has achieved the same speed and taken note of its average light level, they begin to wander about looking for things to illuminate. Because all the lights have gone through their training by keeping track of time, they express this orderly understanding by blinking their red LEDs in unison about once every 5 seconds. So we'll play that one. This represents the calibration or socialization process. That's the start of the universe right there. They're training themselves to run at the same speed regardless of individual differences. He's trying. No, we didn't get the rest of that. Could we go back and... Well, this is the last image, and what you see there is bad behavior. I'll go into that. We missed a little bit of the second to the last movie, so if we can go back to that after this. I think it's still running in the background. I'm putting a very good tech movie through a real stretch here. Maybe if I go back. Here we are. Do we have time to play that one more? 1 minute? Let me go through them. All right, well, this doesn't take 4 minutes, so if you could play that one movie again. Oh, you know what? That's the bad behavior. I'll just describe what you've seen. Okay, yeah, more bad behavior. The watchful state involves rambling and looking for things to illuminate. If a bald head appears under the rambling light, it stops rambling and illuminates. You've seen that. If several lights coming from different directions also sense something and illuminate it, they give a superficial appearance of emergent behavior. So far I've described the physical network of proximity, where each light only senses its nearest neighbor, and the obstacles, and something below. But an extra social behavior was also programmed into each light, a network of signals. If no bald head shows up under a light for 2 minutes, that light enters a state of anticipation. This is expressed to observers out beyond the universe by blinking their LEDs every second. In this state, if a bald head appears under the light, it beacons to all the others, and they all stop what they were doing and come swiftly in that direction. Amidst all this calibration, socialization, and rambling, certain kinds of bad acting do arise. They're a kind of emergent behavior that depends on infrastructural accidents and random reincarnations and subsequent recalibration errors rather than my programming errors. Infrastructural accidents happen when a dense clustering of lights causes the supporting rods to bounce too much, which then causes a reboot in a single light, and it goes into its own private, late recalibration and a warped sense of resocialization. This light goes through this very constrained calibration sequence because it's being buffeted by the normal behavior of all the other lights. So despite careful training in the appearance of socialization, bullying behavior also emerges, with a more sensitive light trapping a less sensitive light against a wall, causing it to oscillate back and forth until it shuts down. An error trapping routine was built in to prevent harmful behaviors from damaging the whole system. Both the bully and the bullied lights have to go on timeout at opposite ends of their universe until the next universe happens. So with that, I'd like to end with a nod to Marshall McLuhan. If it works, it's obsolete. Thanks a lot. Any questions? like Candide says at the... Yes?
So your nail didn't actually go through the lines again?
They do, once a day. Except they have aging bodies. So if you can imagine, you know... That's right. The motors get older and there's more friction. Yes? Absolutely. We need to do it.
We develop here, what happens?
Well, they stop paying attention. Yes?
I think some of us got a little seduced by your wit and forgot, why are you doing this? Would you...
That's a fascinating question. I'm very interested in having buildings that have really low-level intelligence that can take care of certain environmental issues all by themselves, that have fun doing it, while we're inside having our own kinds of fun. I can imagine a building that knows to go on the market and do shorts for energy costs. I mean, as energy costs rise, buildings should be making their own decisions about what kind of energy to be using. And so they can have their own fun as well. I just don't want them to be too smart. That's why I use collections of very, very dumb processors, because I don't want them coming after me. Yes?
Do you have any thoughts on using this for either rehabilitation or education, where the people become engrossed or feel association with the behavior and they want to see it continue, or they don't want to foul it up, or they want to make it stronger or better? And so it's through the interaction that either education or rehabilitation is facilitated?
Yeah, I have two short answers to that. One of them is that I would like to see a subsumption architecture, Anita Flynn's concept of a higher level of interaction by people who live in the building from time to time, who could give change some basic parameters and say, you know what, I really don't want to buy that gas from that particular country. I'd really rather go in a different direction. But with respect to rehabilitation, one of my partners on this project, Michael Peshkin, Dr. Peshkin of Northwestern University, has invented a robot that actually follows behind people who are relearning to walk and grasps them only if it senses a stumbling about to occur. And it's a very similar kind of an intelligence that he built into those robots.